So let's discuss some of the comprehensive type of questions for mechanics of fluid. So the very first question, the torque required for rotating a disk of radius r, constant RPM of n, or a flat plate with fluid with thickness h and viscosity mu. We have to find a torque of a disk which is having a radius which is rotating in a flat plate, and the parameters of the flat plate is which is that flat plate is having a thickness of h, and there is a fluid inside that flat plate which is having a viscosity mu. So we have to find the torque required to rotate in that fluid. Okay, so that rotating disk, the torque required for that in order to rotate in it. Okay, we have various options. So let's look at how to solve this and what is the correct formula of this condition. So this is how does it look like? We have a disk of some particular radius. This is just a similar case, just like what we asked. We have a flat plate having some thickness, and this whole disk is rotating inside a flat plate of thickness h, and there's a fluid inside it having viscosity mu. So this is actually in circular in structure, but we have taken the cross-sectional section in view. So it may appear rectangular, but actually that the part in the fluid is actually a circular disc. Okay, so this thing is rotating inside that flat plate. Okay, so inside a fluid having viscosity mu. So we have to find how much torque required to so I mean take it to rotate inside it. Okay, so what is the correct formula? So this is a fixed condition. Okay, in order to find the torque required to rotate the disk of radius capital R at a constant RPM n, okay, or a flat plate having a thickness h and dynamic viscosity mu, you can simply use this formula phi mu r s to 4 uh, tau by, it's actually omega, but that is substituted by another formula. Anyway, the representation is angular velocity by 2 pi h. So this is a fixed formula of this condition, that is the torque required for a disk having a radius r at a constant rpm n. Okay, so having a thickness h. So that the raw part we have to substitute the angular velocity as 2 pi n by 60. So the final formula for this condition would be, this is the final expression for torque required to rotate the disk is equal to pi square mu n r s to 4 by 60 h. This formula is formed after substituting the value of angular velocity as 2 pi n by 60. This is the previous equation of torque. So this is the final formula of this condition of a disk rotating inside a plate having thickness h and viscosity mu. So this is the torque required to rotate inside that fluid. So next question is the location of center of pressure over a surface immersed in a liquid. Okay, we have to guess where is its location with respect to centroid. A always above the centroid, B will be at the centroid, and C always below the centroid, and D above or below, and depends on density. Okay, so let's look at how to solve this one. So the center of pressure is the point on a submerged surface or your immersed surface where the total resultant hydrostatic force act. Okay, center of pressure means the total hydrostatic force acting on that body is concentrated at that particular point. Okay, and what is centroid? Centroid means a geometric center. Okay, the body can be either cube, it could be a cylinder. It varies on different geometry. So whatever it is, centroid simply means a geometric center of the surface, and that's the point where the average pressure act. Okay, center of a body means that at that particular point, average pressure acting on body is concentrated at that particular point. That is what centroid. So the center of pressure is where the hydrostatic force is acting, right? So center of pressure would be increasing with the distance. Okay, p is equal to rho g, and so it would increase with the distance. So it would be maximum at a very lower part. So that hydrostatic force, rho g h, p is equal to rho g h is what is hydrostatic force, and it has to be increases with the distance. So by applying simple logic, if you just think then if it has to be maximum, pressure is maximum at the very bottom of the surface, and if it has to be maximum at the very bottom, the distance should increase. So obviously the central pressure would be at bottom. So central pressure is located below the centroid. Okay, geometric center, because the pressure increases with depth in a liquid, right? By that formula rho gh. Okay, it has to increases with directly proportional to that distance. Okay, the pressure distribution is not uniform. It is higher at the greater depth and causing the resultant force to act at a point lower than centroid. So any body immersed in a or submerged in a liquid, its central pressure will be always below centroid. Okay, sometimes the centroid and the center of gravity could be same. Okay, it varies on the density. If we consider a body of uniform density, obviously the centroid and the center of gravity coincide. It would be the same thing. If we consider a body of uniform density, same material throughout, then the center of gravity and centroid will be same. Such bodies. Okay. So in general, central pressure is always below centroid. Okay. So this is how it will look if I have shown you a figure. As you can see that P is the point of center of pressure and G is the center of gravity. Okay, here they are considered an element not to depict how the center of gravity and center of pressure shown. But in general, that the center of gravity and the centroid would be same if we consider a body of uniform density. Okay, I am considering, suppose I am considering same body. I have immersed in water, then at that point, one with having same density throughout, then the center of gravity and centroid would be same. Okay, anyway, that center of pressure would be always less than center of gravity or centroid. Okay, so next question: the sphere of radius or m radius is immersed in a fluid with its center at a depth h meter. Okay, the vertical force on sphere will be, okay. So we have to find the force acting in the vertical direction on this given sphere. So the force acting on this body will be buoyant force. There are various other force: weight of the body, surface tension, hydrostatic force, but they are more concentrated on a surface. But in this question they are asked to find the vertical force acting on the body, the whole body. So we will be considering the suitable answer will be buoyant force. Okay. So we know buoyant force is simply equal to the weight of the body itself. Weight of the body is mg, where m is mass. So mass is the density into volume. So buoyant force equation Fv will be density into volume into that acceleration due to gravity. Okay, so we have the equation for Fb rho Vg. Then next step is we have to find the volume. Okay, so the volume V of the sphere with the radius capital R is 4 by 3 pi r cube. Okay, that's the volume of sphere, which is 4 by 3 pi r cube. What's next step? Substitute this value to the previous buoyant force equation. So after substitution, on the place of V will be rho into 4 by 3 pi r cube into G. So the final expression of buoyant force would be 4 by 3 pi r cube rho G. Okay, 4 by 3 pi r cube rho G. But in our question, there is no rho G. So they mentioned gamma. So what is gamma? Gamma is specific weight. Okay, specific weight is gamma, and in fluid mechanics, it is represented by gamma, that is denoted by gamma. And gamma is simply rho G. Okay, it is the product of density of the fluid and the acceleration due to gravity. Rho G is gamma. So the final equation will be, so we have from that expression, the answer will be option A, that gamma is a specific weight. So we got 4 by 3 pi r cube rho g, and the rho g is substituted by gamma. Gamma is a specific weight. So our answer is gamma 4 by 3 pi r cube. Option A.